my name is Jeremy Douglas. I've taught physics for about 15 years, and this Physics Partners video is about Newton's third law. Now, when we meet Newton's third law, we always meet this phrase, you know the one. For every action, there is an equal and opposite reaction. This is a very memorable phrase, so it's nice for that reason, but it does have certain drawbacks. For a start, it uses the word action instead of force. And then it can lead to some serious misconceptions in your pupils. Probably the main one of these is the idea, how can anything ever move or accelerate if every force has an equal and opposite force cancelling it? I actually find a traditional note very helpful here. I say to my class, this is absolutely correct, but here's a more accurate and detailed way of writing it down that will help you to use this law successfully. They write down this, Newton's third law. If object A exerts a force on object B, then object B must, and I do get them to underline it, and I do repeat the word because this, as far as we know, is a universal law. It always happens. Object B must exert a force of the same size, equal, fine, but also of the same type. In other words, if one force is electrical, the other force is too. If one force is a contact force, the other force is too. If one force is gravitational, the other one is too. In the opposite direction, equal and opposite, most importantly, it's on object A. And this is another thing that I get them to underline, emphasize, make a silly animation of, because it's so important. One of the forces is on object B and the other force is on object A. The two forces are on different objects. That's why they don't cancel. I'm sticking these two toy train carriages together with a bit of sticky label, but it's not that sticky, as you can see. Let's analyse this situation in terms of Newton's third law. So here the magnets, which you can see in the middle, are repelling each other. The left-hand carriage, the yellow carriage, exerts a force to the right on the green carriage. It's a magnetic force. The green carriage must exert an equal and opposite force on the yellow carriage, which is also a magnetic force. That's Newton's third law. And that's why when the label loses its stick, the two carriages spring apart because of those two forces acting on the two carriages. A few more examples of the thought you might find in a textbook. A swimmer pushes backwards on the water. What's the third law pair? Well, the water pushes forwards on the swimmer. A plane pulls forward on a glider. The glider pulls backwards on the plane. The Earth pulls gravitationally on the moon. The moon pulls gravitationally on the Earth. Three third law pairs. Please note that in each case, the nouns have switched. We have the swimmer and the water and the swimmer. The plane and the glider and the plane. The Earth and the moon and the Earth. This is an extremely well-known demonstration, but none the worse for that. Drinking straw on a string, balloon. I find it works best if you don't blow it up too much. Sticky tape. We attach the sticky tape and the balloon to the drinking straw like this, and we let it go. The balloon pushes the air to the left, and the air pushes the balloon to the right. Newton's third law. Here's the balloon. It's pushing the air to the left, and so the air must push the balloon to the right with an equal and opposite force. The balloon's propelled to the right. This is how a rocket works. Notice that the balloon is pushing against the air that it expelled. It doesn't have to be pushing against the atmosphere. A rocket can fly perfectly well in a vacuum. It pushes against its own exhaust gases. What about this situation? Deep space, astronaut, oxygen cylinder. Astronaut pulls on the oxygen cylinder, a pulling force via the rope. What's the Newton's third law of pair? Pause, think. The oxygen cylinder pulls the astronaut to the right with an equal and opposite force of the same type, tension in the rope. Now, the oxygen cylinder is probably less massive than the astronaut, and so it will accelerate more. This is one of the most classic third law problems there is, a falling skydiver. What is the Newton's third law pair to the skydiver's weight? Now, whenever I ask a class this, 99% of the time, someone will say, oh, that's very easy. It's the air resistance force, R. But that can't be correct. I want you to pause the video and think about why can that not be the correct answer? There are 3 reasons it can't be the correct answer. Number 1, it's not of the correct type. It's an air resistance force, but the weight is a gravitational force. 2 forces must be of the same type. Also, Newton's third law says the 2 forces must always be equal, but the air resistance will only equal the weight under certain circumstances, if terminal velocity has been reached. Most fundamentally, though, these 2 forces are on the same object, and Newton's third law says the 2 forces must be on different objects. So for those 3 reasons, the air resistance can't possibly be the Newton's third law pair to the weight. What is the correct answer? Again, pause and think. Well, the weight force is the force exerted by the Earth on the skydiver, and so the Newton's third law pair must be the force exerted by the skydiver on the Earth, the gravitational force exerted by the skydiver on the Earth. Why doesn't the Earth therefore then fly up towards the skydiver? Because it's so massive. The force, although it is the same size, has much less effect on the very massive Earth. Now, the air resistance force does have a force of its own. That is a Newton's third law pair of it. The air resistance is the force of the air on the skydiver. And so the Newton's third law pair to that will be the force of the skydiver pushing the air downwards. Another example, a block on a table. What's the Newton's third law pair for the block's weight? Well, it's tempting to say the contact force, but that can't be right because not only is it not of the same type, it's also on the same object. You often see these contact forces being called reaction forces. I try to avoid that because it invites this very misconception. I try to call them contact forces or normal contact forces. The Newton's third law pair must be on a different object. It's the gravitational pull of the block on the Earth, which is the counterpart to the gravitational pull of the Earth on the block, aka the weight. Of course, the contact force does have its own Newton's third law pair. That would be the contact force of the block on the table. The 2 red arrows are a third law pair. The 2 blue arrows, they're also a third law pair. Newton's third law comes up all the time in physics. It's a really fundamental concept and it's really easy to get wrong. So if your pupils can understand this successfully, you will have done them a huge favour.